In this problem, we're looking at two immiscible liquids, water and normal octane, at 85 degrees C, and we're going to heat them at constant pressure to 130 degrees C. And what we want to plot is the partial pressure of N-octane as a function of temperature. And we're giving the normal boiling points of water and normal octane at this pressure. And so to help solve this problem, the simplest way to approach it is to first draw an approximate diagram of what temperature versus mole fraction looks like for this system. So we're going to plot on this graph 100 degrees C, so at mole fraction of 1, this is water, so 100 degrees C, that's Tsat for water. Over here is in octane, and 126 degrees C is Tsat in octane. Now we're starting at a mole fraction of 0.3, 85 degrees C. We know it's liquid there, so at some higher temperature we start to vaporize. Let's approximately say it's around 90 degrees. We don't know, but the idea is that we're going to have what the diagram looks like is something like this. I'm just drawing an approximate diagram because this is an approximate plot. So something like this, maybe it's higher than 90, maybe it's lower than 90, but it's in that general area. And so between 85 and 90, there's no partial pressure because we have no vapor. We start forming a vapor here, and the mole fraction of water is 0.68, which means the mole fraction of N-octane 0.32, and since the pressure in the system is 1 bar, that means the pressure of NO then at that point 90 degrees 0.32 bar. And we get to 95 degrees, we have now only normal octane in the liquid phase. All of the water evaporated at 90 degrees, and the mole fraction now of water about 0.6, so the mole fraction of normal octane 0.4, which means the pressure in octane is 0.4 bar. At 105, same reasoning. The mole fraction of water is 0.44, so the mole fraction here of in octane 0.56. So that means at this temperature, pressure of N-octane equals 0.56 bar. And at 112 degrees, we vaporize everything. Mole fraction of N-octane 0.7, so pressure of N-octane is 0.7 bar. And at higher temperature up to 130, only vapor, the partial pressure doesn't change. So let's look at what these values look like. We plot them. So let's look at the N-octane partial pressure versus temperature from 85 degrees to 90. There's no vapor, so it's 0. At 90 degrees C, the mole fraction of the vapor, and therefore the partial pressure, is about 0.32. So it jumps up to this value, and then at 95 degrees, we said it's about 0.4, and 105 degrees, about 0.56, and 112 degrees, it's 0.7, and then it remains constant as we raise the temperature above that. So here's how we expect the partial pressure of N-octane to vary as a function of temperature. Just an approximate plot. We can also do the calculation using the Antoine equations for saturation temperatures. And if we do that, first here's what the temperature mole fraction diagram, mole fraction of water looks like. And here's what the plot looks like with the accurate values.